Okay, let's get started. So let's see, where are we in the class, in the course? We are here. A week from today is the midterm test, midterm exam. We are a little bit behind schedule, but don't worry about it. However, there is a complication. I'm going away to a conference next Monday through Wednesday, so I won't be here on Monday and I won't be here on Wednesday. And I'm sorry about this because I feel like I'm abandoning you at your time of need, but hopefully it'll all work out. So firstly, well, on Monday, I think the best thing to do is for you to watch some videos from the previous times I've taught this class. There are a couple of videos I want you to watch. One is this material on phase and group delay, which is part of this slide pack, but we're not going to do it today. But it won't. I need you to see this at some point because we're going to refer to it, but it won't be in the midterm. You don't have to have mastered this material to do the midterm. The second part is this actual video of the corresponding lecture from last year, which will be finishing off the material that we looked at today, and also some sort of discussion of the big picture and going over the example midterms. I'm going to send all this out in an email, so don't worry about taking this. I'm just trying to explain what's going on here. So that'll be Monday. There won't be anything happening here, but you can watch those videos in the time that you would normally have been here. Then on Wednesday, it's the midterm, and again, I won't be here, so what I've done in the past in this situation is have someone come in and just sit with you while you do the test. But of course, we have this added situation that we've got quite a full class, and it's going to be it would be quite chaotic to have 100 people in here sitting the midterm. So what I've decided to do is to have it be effectively a take-home midterm, but very, very limited time window. So basically, the midterm it's meant to be something you do in the class session, so it's a 75-minute test. But you won't have to do it here. I'll let you, you can just do it wherever you want. So the plan is I'll put the midterm questions up on the website 9 o'clock Wednesday morning. You schedule the time, which will presumably be this slot, to sit for 75 minutes and to do the midterm, and then you have to submit your completed script to my lab, to Lab Rosa in SEPSA by noon, right? So we have to have it in our hands by noon. Now, obviously, the midterm is already open book, right? So there's no issue about what you're looking at, but it does need to be your own work, right? So I'm trusting you. I'm putting it on your honor that the script you submit is your own work. Generally, I try and encourage you to collaborate, but in this, because it's going to contribute to your grade, I want it to be your own work. Hang on a second. And also that you've just taken the allotted time, the 75 minutes, right? Because if you take longer than that, then it's not fair on other people. So, if we were in here, I could sort of try and control that. I could certainly control the amount of time you spent. I could try and control you from not looking at other people's work, but actually it wouldn't be very easy because it would be so crowded in. So I'd rather do it, on the honor system. You had a question, yeah?
Yeah, what do you mean by script?
Your work. So it's not MATLAB, it's all just pen and paper. A script is like, I don't know, when I went to university in, my medieval British school, that was what they would call the exam, a script. So just because I guess they wrote it in script. Yeah.
And where do we turn the homework then?
Right. So the homework, which was also going to be which is due on Monday, should also be submitted to the to Lab Rosa, to my lab, which is where you pick up the graded homeworks, or where Darwin has his office hours. So you can just drop them in on Monday or whenever. Yeah.
Do you have to submit it at that hour, or can we just go on the weekend and just?
Oh yeah, you can submit it anytime. I mean, there may not be anyone there, but you can try and fit it under the door, or you can, whatever. Great. Okay, so that's Monday, Wednesday, and then, so the homework, this week's homework is due on Wednesday, and there's no homework being issued today, right? So there's no homework due for next week, obviously, but yeah.
Can you explain more? So can we Google, like, can we use Wikipedia and stuff?
I've never thought about that before. Can you use Google and Wikipedia? So here's the problem, right? I don't mind. I have no problem with you looking up those materials, because that's kind of like just a generalization of textbook. But I would not. But I don't want you Googling like the question. I mean, not that the questions are out there, but just like, I could imagine resources which says, I've got this question. What is the right way to answer it? And that there could be a large number of resources out there like that. So I don't want you doing that. I don't suppose it would help, actually, but I just, I'm just saying that's not okay, right? So trying to directly find the answer to the question, which is sort of one step away from asking someone else to do the question for you, asking another person to do it, that's not okay. Using online resources is okay.
And the homework solutions?
Homework solutions, that's fine, right? Because they would be something that you could have printed out and brought with you if you'd wanted to. It's a very, this whole process of evaluation is very tricky. But hopefully we'll be able to make sense of it. It'll be fine. Thank you for clarifying that. Okay, so I'm going to send out an email explaining what I just said so that everyone knows what's going on. If you see any real problems, or if you feel very unhappy about that, then let me know. We could still change it, but I don't expect to have to change it now. But that's the plan at the moment. Any other comments? Okay. So I feel like we're sort of we're at the end of this kind of arc, that we've gone through this set of ways of talking about the problem we're interested in of signals and systems, and then talking about these different ways of understanding it, the different tools we have in the time domain, the frequency domain, and the Z-transform. And we've sort of gotten through it now, but we haven't quite landed back at home. We've still got a little bit of work to do closing the loop. And I'm hoping that in the material which I present today, we'll do that, and then that will make you feel like, oh, okay, now we're in this stage of trying to tie together the big picture. And basically that is, well, we've got all these. We've got these tools, the Fourier transform, the Z-transform. What we did last time was this thing of calling it the transfer function, which is basically expressing describing the system through its Z-transform, but interpreting that as a as a map as the Fourier transform, and so that gives us directly from the difference equation, gives us this polynomial, which we can then evaluate on the unit circle, which gives us the frequency response, right? So that was, the polynomial is a nice way to think about it because it gives us these roots, the poles and zeros. The poles and zeros go directly to this intuitive understanding of where the peaks and valleys are going to be in the frequency response, which is the unit circle and Z-plane. And so then we can understand what's going on in a system. And then I went through this, in the idea of the sort of rubber sheet description of the z-plane is the same as this geometric interpretation where the actual value of g of z for z equal e to the j omega is just the product of the numerator terms divided by the product of the denominator terms. And you can interpret those as vectors between the point of the unit circle and each of the poles and zeros. And so then you get these effects where you can think about the influence on the magnitude response of individual poles and zeros. And then you can understand the overall behavior of some system with some set of poles and zeros as the combination of all those the influences of the individual poles. And that this means that if you have something like this, so once you sort of got this, then if you have a picture like this with some poles and zeros and you think, oh, they're close to the unit circle, so I think they're going to have influence, they're going to have some kind of effect over here, but they're close together, so I think they're going to sort of cancel out elsewhere. And I see that the pole is closer to the unit circle than 0 here, so the pole is going to, the gain due to the pole is going to be, it's going to overwhelm the attenuation due to the 0 here, so we're going to get a peak in the frequency response. So the idea is you can go straight from that picture to an idea of what that's going to look like. Yeah?
I can understand how to do that for magnitude, but I'm a little lost when it comes to phase.
Yeah, I've stressed it much more for magnitude than for phase, and that's kind of, that reflects the sort of the bias of the whole process of filter design, which is very often we go for magnitude first and then let the phase be what it will. Now, in different situations, you might care about the phase, and you might have a different priority. There's nothing more. It's not more complicated for the phase. It's just that I just don't talk about it very much. But the phase of the individual components, right? So the phases all multiply together, or in the phase domain they add up because the phase is the exponent of it's e to the j omega, e to the j theta. So if we can calculate the phase of each of these terms, we sum up the phases of the phases due to these ones. We subtract off the phases due to these ones. And so the phase is just of this little vector, it's the angle it makes with 0. So here the phase due to this 0 is, something like pi on 4. The phase due to this 0 is closer to pi on 2. And then the phase due to this pole is a little bit less than pi on 4, which is subtracted off. And this one's a little bit more than that one, which is also subtracted off. So you get these phases. The phases tend to cancel out, but in the region of the pole, right on the pole, these ones would be equal. Here's the way to think about the phase. What's interesting about the phase is how rapidly it changes, right? And when you've got this little point in here where you've got this point moving on the unit circle, and it's moving, its magnitude is not changing very fast here because it's sort of a point of closest approach, but its phase is changing the fastest because it's the point of closest approach. And the phase due to the pole is changing almost twice as fast as the phase due to 0 because it's half the distance. And so the phase due to the pole, which is because it's the phase is getting larger, right? The angle, this vector is winding this way, so the angle is getting larger. But when it's the phase due to the pole, it's negated. So it's the phase is getting more negative more rapidly than it's getting more positive. And so that's where we see this kink here, where the phase goes down locally. But then the baseline value on which that negative slope occurs depends on the actual values of these different angles. Right here, the phase due to the pole and the 0 are the same. So that's the sort of a 0 point in here, and the phase due to the pole and 0 here are kind of the same. So actually at the center frequency, that's almost exactly the 0 crossing point of the phase here. But then it's got this negative slope, and then if you work it through, that implies there has to be this sort of positive bump beforehand and stuff. So that it all works out. But you can get often, as you'll see when you see the group delay stuff, we're very interested in the local slope of the phase response because that gives us this effective delay of signals in that range. And so that's why you care about the derivative of slope with the derivative of phase with frequency quite a lot. Okay. So that's again this picture of the slope with the red circle on it is the same. It's the same math as the vectors getting closer and further away. It's just a different way of looking at it, of visualizing it. and that the sort of the rules of thumb are all about poles, how far they are from the unit circle, and where their relative positionings are. Okay, so this is now we've got this idea that we can go from the Z transform, which is a polynomial whose coefficients are actually just the values of these gains in this delay and gain flow diagram. We can go from there to the frequency response. That means that now we can talk about actually building systems that have particular frequency responses that perform particular operations on a signal interpreted in the frequency domain. And that's what we call filtering. I mean, there are many different readings, meanings, interpretations for filtering. But the kind of filtering we're specifically interested in is this idea of modifying a signal in its Fourier representation in the frequency domain. The reason why that would be useful is because, we believe that if we have a situation where there's some parts of the frequency domain which contain information we care about, and other parts that contain information we don't care about in the time domain, those things are going to be superimposed. They're going to be hard to separate. If we go into the frequency domain, they're separated. Now we can remove the parts we don't care about, just keep the part we care about, and then if we're back in the time domain, suddenly now we can test for the presence of a signal simply by looking at its magnitude, for instance. So here's an example, right? We've got two components here, A cosine omega 1 n plus B cosine omega 2 n. Omega 1 and omega 2 are different frequencies. A and B are different kind of amplitudes, and we don't know what they are, and maybe we want to know, there's information carried in those. But this part is basically interference or noise, and this is the part we're interested in. So we'd like to build a filter that would remove this part and keep this part, so we could just examine what A was without being confounded by variations in B. And so here's a frequency domain view of this. If these are cosines, then it means they have, in the Fourier transform, they're composed of a plus omega and a minus omega component, right? Because cosine is e to the j omega plus e to the minus j omega, with amplitude a on 2 in each of them. So here's our A component, omega 1, and let's say omega 2 is larger. So here's our B component at frequency omega 2. And if we could build a filter with a frequency response h of e to the j omega that looked like this, so that it was close to 1, say, in the region of A, in the region of omega 1, and close to 0 in the region of omega 2, then when we pass this signal through this system, right, we take this spectrum here, the blue and the green, which is the spectrum of our signal, x, we'd multiply it by h in the frequency domain, and then the B components would disappear, and we'd just be left with the A components. That's classic filtering. That's what we're all about. So what we want to do is somehow build this H, come up with a system such that its frequency response, its magnitude response, h of e to the j omega 1, is around 1 in the region of omega 1, and it's around 0 in the region of omega 2. And that'll give us a graph that looks something like that, that'll do what we want. Because then when we convolve h with x to get y, that'll be multiplying them together in the Fourier, in the transform domain. So we'll get something. If the magnitude response is actually 1 here, it'll be just A cosine omega 1n, maybe plus some phase response from the system here, because we haven't said anything about that. But if we're just going to sort of look at its peak amplitude, then we could just get A straight off by looking at the time domain. And so obviously, if we actually computed a DTFT or a DFT, we could just look at these components and we could read them off, and we wouldn't have to design an H at all. But the idea is, by thinking about it in frequency domain, we're going to design an H, which is actually a time domain implementation, time domain system, an impulse response, that we can then implement this whole thing in the time domain without having to go to the expense of computing the Fourier transform. And then we'll have a time domain signal, which is this, which again we can just use to extract our feature of interest. Well, now we know something about what h of e to the j omega is going to be, from our analysis of the transfer function. So we should be able to design a system that has the h that meets those criteria. And of course, there are many different systems. So we have to start with a system family first. So let's start with this family of second order feed-forward, meaning finite impulse response systems, with symmetry. So the symmetry is that the first and third terms are the same, and the second term is independent. So this is our block diagram, how we build it with 2 delays, 3 gains, and a summer. And this is the impulse response of the system, right? If we put an impulse in here, at time 0 we get alpha coming out. At time 1, the impulse goes down here, we get beta coming out. At time 2, the impulse goes down here, and we've got this same alpha here, so we get alpha coming out. And then time 3 and beyond, there's nothing happening. It's the system is all 0 again. So we just have this nice 3-point impulse response, which is the characterization of the entire system. But we've got 2 parameters here, alpha and beta, which we can control, which we can set. So if we have this system with this impulse response, what is its frequency response? Well, we can take the Z transform and evaluate that at e to the j omega. The Z transform is just going to be this, alpha plus beta z to the minus 1 plus alpha z to the minus 2. And then we evaluate it at z equal e to the minus z equal e to the j omega. Or which is the same thing as just taking the DTFT directly. So DTFT is just the sum of h of n e to the minus j omega n, which here, because h of n is just these 3 non-zero points, just gives us these 3 terms in e to the j omega. We can rearrange this to make it so that we can separate out the magnitude and phase terms, right? So if we pull out, this is actually this in the Z transform, this would have been a second-order polynomial in Z. In the e to the j omega formulation, this is a second-order polynomial in e to the j omega. So if we actually divide out in e to the j omega, we're left with alpha times e to the plus j omega plus beta plus alpha e to the minus j omega, right? This, which we can rearrange as beta plus alpha times these 2 e to the j omegas. Now we see why the symmetry was a nice thing to include here, because now these terms collapse into 2 cosine omega, and we're left with an h of e to the j omega, a transfer function which is just a pure phase term, a pure linear phase term, e to the minus j omega, and a nice real magnitude term, beta plus 2 alpha cosine omega. So the magnitude response of this system, or this family of systems, is just the magnitude of beta plus 2 alpha cosine omega, but we've still got these 2 parameters in here. So although it's going to be, the beta term is going to be a constant offset, and the cosine omega term is going to be some kind of function of omega that has a cosine shape, we can set their relative heights, which means that we can actually control, the value of this function for some values of omega. So for instance, if we actually had this problem of trying to separate 2 frequency components, the problem we started off with, and if we have particular values for those 2 frequencies, let's say omega 1 is 0.1 radians per sample, omega 2 is 0.4 radians per sample, so it's 4 times faster. What we said was, well, if we can make the gain 1 for this frequency and 0 for this frequency, then we can remove this component and just leave that one more or less untouched, or at least its magnitude is untouched. So we've got our equation for our magnitude response, and now we've got some specific values. So basically we end up with 2 equations and 2 unknowns, right? So we want this thing to be equal to 1 for omega equals 0.1, and we want it to be equal to 0 for omega equals 0.4. And 2 equations, 2 unknowns. We can solve for the alpha and the beta that give us that, and it turns out it's beta equals minus 12.46, alpha equals 6.76. So there's something, this is a slight. This is in addition to what we've done before, but now we're using our ability to write down the actual expression for frequency response, and then to do it, abstractly, including unknowns of the impulse response, to allow us to solve for a particular form of the response. Yeah.
Wait, so you use the DTFT of the signal itself to make the filter?
No, I didn't use the DTFT of the signal. Here's my system, right? So the signal coming in x of n, I've got no idea. I'm not saying what x of n is. In the back of my mind, I'm thinking, okay, x of n is going to have these 2 components at omega 1 and omega 2. But right now, I'm just taking, well, here's the system, here's this impulse response, I'm taking the DTFT of that, right, which is going to tell me what the system is. Now, what I'm trying to achieve, right, if I go on the previous slide, I'm trying to achieve this thing here such that, y of n for some input x of n will be the product of x of n with x of e to the j omega times h of e to the j omega. And so if I have these components here, I want h of e to the j omega to have particular values of these two frequency values. But I haven't. I'm going to end up with a system which I can feed any signal into. But if I haven't feed a signal with these particular components, then I'm going to have this result. So here's the result. I'm going to construct my h of e to the j omega to have these particular values, have these particular magnitude responses at these two frequencies. It's going to have magnitudes at all other frequencies as well, which I'm not controlling. Basically, I've only got 2 degrees of freedom here. I've got alpha and beta. I can vary. And so I can only control it at 2 points. So I try and set it for a third point. I'll have 3 equations and 2 unknowns, and I won't be able to do it. But if I only want to, if I only care about, fixing it at 2 points, then I've got enough degrees of freedom to do that. And it turns out that I even have, the solution I want is within the space of possible solutions I can achieve. So I can build this filter. Let's look at what this filter actually looks like. So here's the filter, right? We said that the impulse response was just alpha, beta, alpha. Alpha is 6 point something, beta is minus 12 point something. So here it is. It's not quite the way we drew it, but it's a 3-point symmetric finite impulse response system. Here is its frequency response. So now I can take this, I can calculate its DTFT, or take this impulse response and calculate its DFT even. And here's what it looks like as a function of omega from 0 to pi on 2. Why is that in rad? I guess I've zoomed in here because we'd specified the actual frequency response in the design was in terms of omega in rads between 0.1 radians per second and 0.4 radians per second. So this thing goes on. But basically that's all we have is this single 0 here and this nice gain response here. What we were trying to get to was a 0 dB gain here, a gain of 1 here, which you can't quite see, but that's where the gain is slightly larger than 1 at DC. At 0.1 radians per sample, it's exactly 1. And then we wanted the gain of 0 at 0.4 radians per sample. This is in decibels, so that's negative infinity decibels, and you can see that it's going down to a big negative asymptote there. So the frequency response did what we want at these two frequencies, and of course it then takes on other values in between these other frequencies. And here's what it does, right? So here's an input signal. The blue line is a sum of these two sinusoids at 0.4 radians per sample, the high frequency, and 0.1 radians per sample, the lower frequency. So again, it's this sort of, you can see that it's the combination of a higher frequency sinusoid superimposed on a lower frequency one. And here's the output of feeding that blue signal into this 3-point FIR filter, convolving the blue signal with this impulse response. And we get this nice, smooth red signal, which is just the lower frequency component, the component at 0.1 radians per sample. There's something weird goes on around 0, which is basically our transient response. But once we're free of that transient response, then we've completely eliminated the high frequency component. Yeah.
So how do you how do you control the rate at which the amplitude falls?
This right here, right?
Yeah. How do you manipulate that? Because if 0.2 is, if the amplitude, you need a bigger distinction between the amplitudes to be able to distinguish exactly the signal you want.
Yeah. Yeah. So that's the right. So the question is like, well, this sort of this shape just kind of fell out of us. We didn't really design this shape. It just like we built this filter based on specifying the gain at these 2 points, and then the shape just happened. But normally, when we're thinking about, in engineering, in signal processing, when we're thinking about filters, we sort of want to have a little more control. Now, the point is that this filter had a very small, had a very limited design space. So we just had those 2 parameters, and the actual equation we had was that the magnitude of h of e to the j omega was whatever it was, beta plus. Beta plus 2 alpha cosine omega. Now, what that actually looks like, right? So that's saying as a function of omega here, we've got the magnitude of h of e to the j omega, and we've got a beta here, and then we're adding to that a cosine term. So if omega goes up to pi here, then the cosine term is like this. Well, it would be around 0, but a cosine term like this, which we're scaling by alpha, and then we're adding those two together. And so in fact, the variation with frequency that we can achieve is only the variation due to this cosine term. We can't sort of scale it. We can't make it, change more rapidly. We can increase alpha so we can make it like that, but we can't otherwise change the shape. And then what's happening is basically the solution we came up with was that beta was actually going to be negative. It was going to be something down here. This was like, minus 12, and this is 6, right? Does that even work? Is that what we said it was? Oh, but there's a 2. Sorry, there's a 2 alpha, which I forgot about here. So this is, if this is 6, then we're actually adding 2 alpha here, so that would be sort of 12-ish. And so what happens is that we wanted to get, we wanted the gain to be 0 somewhere around here. And so here was this is where 2 alpha is exactly equal to negative beta. So when we add them together, we actually get a response that the overall response looks something like this, right? It goes through 0 here, and then it does the rest of its cosine thing down here. So I'm sorry that the diagram is not very clear, but this is 0. And so we basically manipulated this beta plus 2 alpha. We set beta and alpha such that it went through 0 here at omega equals 0.4 rads per second. And then we also wanted it to be 1 here, so that was why the scaling is 6 and 12, because then, down here it's a little bit, the peak here is going to be, we have to scale it up so that it's actually all the way up to 1 back here, because it's going to be a little bit more than 0, but we scale it up so it gets to 1. And so that was all we can do. The 0 is kind of the pinning point, the frequency we want to remove, and then we just scale the whole thing to get the gain that we want at the past frequency. And then when we take the log of that, right, we take that. So then we have this shape. We then take the magnitude of this, so we rectify it like this, and so it looks like that. And then we take the log of it, so that this thing then becomes the negative thing, and that's when we get this shape here. Right? So the fact that this is just an offset cosine is kind of hidden, but that's all it is. That's what's going on. Yeah?
Would you use a separate equation if you wanted to do an entire range of frequencies, like you said?
Yeah. So a more classic kind of filter design would be, say, I want to remove all the frequencies between 1,000 hertz and 10,000 hertz something. That's a much harder thing to express here, because that's not like a set of equations. That's an expression for all of x in here, and you can't easily turn that into a solution for alpha. It turns out that you can't even build a filter like that. It's actually a filter that. So what would that mean? So okay, I didn't do this, but this filter, right? This filter that has the impulse response alpha, beta, alpha has has a z transform which has some roots. The z transform is alpha plus beta z to the minus 1 plus alpha z to the minus 2, which is a quadratic in z, which has this, and it's got no denominator, so it just has some zeros here. Has 2 zeros, and lo and behold, we actually know the frequency response is 0 for some particular frequency. So we know where those zeros are. Here's the z-plane, here's the unit circle, and here are our 2 zeros at omega equals 0.4 radians, which is actually kind of smaller than that. It's somewhere down here. But here are 2 zeros, and so now we've got this z-plane going on. If we wanted to have what you're specifying, which is a filter that has zeros everywhere over some range, it's 0. The Fourier transform is 0 for every frequency. Then what we'd have to have would be a lot of an infinitely dense array of zeros over those ranges. for a finite order system like this, which is kind of all we can build with finite computation, it's going to have a Z transform. The Z transform is going to have a finite number of zeros. Even if we put all of those finite zeros on the unit circle, we're still only getting zeros at a set of discrete frequencies. And so the actual frequency response, we'll see filters like this. But what they end up doing is, having a frequency response that looks like this, where it sort of bumps around because it's being pinned to zero, but there's still some frequencies in between here where it's not actually on the zero, and so it isn't exactly zero. But we can constrain how large those bumps become, so we can get an arbitrarily good approximation to that band stop filter. Okay, great. So I feel like you're asking the right questions. So this is the point about what we're trying to do, that we can, because we know where these frequency responses come from, we can start thinking about how we can construct the systems that do what we want to do. Okay. So that's just to sort of tie that together. That okay, this is something that leads us to the ability to design. And then there was this material on phase and group delay, which I want you to sort of review on video at some point, right? Because I'm saying it's sort of, we'll deal with it, and I'll show you the video, I'll point you to the video, but you don't have to worry about mastering that before the test. So what I want to do now is go on to basically follow on that idea of designing the filters as things that we can control and design to achieve goals, and start talking about this set of examples of a few simple filters, just to sort of get the idea of like how all these different parts tie together. The block diagram of the filter, which basically then gives you the LCCDE or the Z transform, as well as giving you the impulse response, and then those lead to the frequency response, which gives us the properties that we care about. So we're going to talk about a few specific simple filters now. So we said what we mean by filter is, in general, the more general idea of a filter is something that you put something through to remove certain parts. And so in signal processing, it's something you put a signal through to change it in a way, basically to take some stuff out because you have some goal you're trying to serve that will be better served by what the filter does to it. When we're talking about filters which are linear shift invariant systems, that's a highly constrained and well-behaved set of filters which as we remember, are fully characterized by their impulse response, which is the same as saying, which is also fully characterized by their h of z. Of course, if we know h of z, we can get h of n. If we know h of n, we can get h of z. So that's the same constraint. And we said that we can characterize them by their magnitudes and phase responses, the way they modify different sinusoids, because that turns out to be a very stable. It doesn't matter what else is going on. If there's one particular sinusoidal component in the input, then the output will have that sinusoidal component with its gain, with its magnitude and phase modified. And now that we've got these mathematical tools for describing what's going to happen, we can talk about designing them to meet particular goals. There are two big classes of filters that we care about. That sort of, basically they divide into these two sets, which I've mentioned, but let's just be explicit here. The two big classes are FIR, IIR, finite impulse response, and infinite impulse response. So the names are talking about properties of the impulse response, basically whether it goes on for a bit and then goes to zero forever, or whether it goes on for a bit and never stops. The idea is, for any kind of causal system, the impulse response is going to be zero for negative time because it doesn't know that something's going to come in, so it can't output anything before the impulse occurs. But once the impulse has occurred, what happens afterwards may die out entirely in some finite time or might not. And it turns out these things, those properties are exactly the same as whether the system has feedback, meaning whether it has poles in its Z transform realization, or whether it does or doesn't. If you do have feedback, then obviously you can see how a signal would never die away. If you don't have any feedback, then actually, all you're doing is delaying the input and adding it in. And if you have a finite number of delays, eventually you're going to run out, and so you're going to have a system where it goes to zero. you could imagine a system where you have an infinite tail, and then you have a delay, and then you have another infinite tail which cancels out the first one. So there could be some systems which have feedback which end up having impulse responses that at least theoretically go to zero. But those things, you'd probably be able to construct them equivalently using no feedback as well. So, you know, there's not an absolutely rigid guarantee that if you've got finite response, you've got no feedback in your system. But for all intents and purposes, these things go together. So let's look at some of these simple filters just to get us going. Now, obviously, we've probably all come across the concept of these filters before. You know, the question about the bandstop filter shows that. So we have these general classes of filter like low pass and high pass, which basically talk about the idea of removing the high frequencies, removing low frequencies, or selecting for particular frequencies. So we start off with a low pass filter. It's going to be an FIR low pass filter, so have a finite impulse response, and it's going to be the simplest possible FIR low pass filter, which is a 2-point filter whose impulse response is the same for both of its two non-zero points, and we'll make it a half, just because that means that its DC response is 1. So here it is written as the a notation for an impulse response to the sequence. Here is the plot of the impulse response, which is the most natural, the easiest way to think about it. So it's 0 everywhere, except at time 0 it's a half, at time 1 it's a half. Everything else is 0. We can take its z transform, right? So z transform is just sum of h of n z to the minus n. So that's just a half plus a half z to the minus 1, like this. It's really just a numerator in it's just the if we write it as a rational polynomial in z to the minus 1, it's just a numerator. If we just try and make it in terms of z, we can divide through by z, but basically all that's happening here is that this thing goes to 0 when z is equal to minus 1, and maybe it has some poles at z equals 0, but like I say, we ignore those because they're just delays. So here's the pole 0 diagram. No one's going to mark you wrong for putting poles at 0, but no one's going to mark you. I hope no one will mark you wrong for not putting them in if they're technically there. We have a 0 here, and then what's the frequency response? That's kind of why we're doing this. The frequency response, we can just take the DTFT of this, or we can write down our z transform using eta j omega for z, and if we do that trick of like dividing out the half of the eta j omega, 0 plus e to the minus j omega, e to the 0 plus e to the minus j omega, then we get an e to the minus j omega on 2 and a cosine term coming through here. And so now we can plot that. We can plot the magnitude of this. This term disappears, and we just rectify the cosine, and we get a rectified cosine magnitude response. And this is, this is a low-pass filter. The highest frequency we can represent without aliasing, which is pi radians per sample, has a gain of 0. There's a gain of 1 at the lowest frequency, a constant value, and it rolls off in between. Yeah?
Looking at that transfer function, the z plus 1 over 2z,
yeah.
Doesn't that have a pole?
Yes, has a pole at z equals 0. Right.
Oh, and finite equal responses don't have poles.
Okay. Finite impulse responses don't have poles except at z equals 0 and possibly z equal infinity. Yeah, I mean, you're absolutely right. And I kind of gloss over that. It's like, wait, we're talking about the z-plane, and you're saying, oh, it's really interesting where these roots occur unless they're at 0. It's like, well, what 0 is right there. It's not like somewhere that we're not looking at. Why do we not care about that? I don't have a particularly good answer for that. The real reason is because actually I don't particularly care about the z-plane. I only care about the unit circle. That's the DTFT. And the interesting thing about a root at the origin is it's the same distance to all the points on the unit circle. So if we're thinking about these vectors, the length of these vectors, there's no variation in length of this vector with omega. So they don't have any impact on the magnitude of the DTFT. They affect its phase. They affect its phase in a fairly boring way as well, because the phase is just the actual frequency itself. So it's a linear phase modification. That's the same as saying if I have some system with a z-plane poles and zeros, which has either poles or zeros at 0, I could shift it in time. I could delay it or advance it, which is multiplying the entire z transform by z to the minus n0, until, which is adding or subtracting poles at 0. I could do that until I got to a point where there were no roots at 0. So there's a z transform which has the same impulse response that's just shifted in time, but has no poles at 0. And it's, apart from that time shift, it's got the same magnitude response. It's got very similar behavior. So I think, what would that look like? So if I just had a response that was z plus 1, right? So it was just the 0 that I care about. That would mean its z transform was, its impulse response would be the inverse z transform of that, which would be like, well, that's the z transform of a system that has a 1 at n equals 0 and a 1 at n equal minus 1. So this would be this thing shifted over back here. And so it wouldn't be the causal version. It would be the thing that has a one step look ahead. I wish I had a better answer as to why that's not the most natural one to come up with. But I don't have a particularly good answer why we use negative powers of z rather than positive powers. That may be sort of lost in the history of how we got here. But I'm saying that system is not particularly interesting. It doesn't have particularly interesting different properties from this one. And this one does have the interesting property that is actually causal. So, but I think, from the point of view of cleanliness, there should be a pole in there. But from the point of view of help getting you onto the track of, let's focus on how these things are actually used, I'm leaving it off just so that we can deal with that question. And so it doesn't affect this plot at all. It doesn't make any difference here. And in fact, it would. This is, notice that this is a linear phase term, which we said if you delay a signal, its Fourier transform. If you shift it in time, its Fourier transform is modified by a term like this. This corresponds to a delay of half a sample, right? The delay, if you delay it by n0 samples, the Fourier transform becomes e to the j omega n0 times whatever it was before you delayed it. So this is a delay of 1/2 sample, which is not meaningless, right? It's saying, well, if I put an impulse in here, I've sort of delayed it to be an impulse that falls halfway between 0 and 1, which of course means that it's not actually on a sample time. But I've also blurred it because I've got this low pass. I'm sort of smoothing it out. And so it becomes this impulse which is centered here but is blurred out. And so I get these two points coming out here. So that completely makes sense, that this system has some kind of magnitude response which is low pass, and then a delay which is half a sample delay. Yeah?
Sorry, why is omega limited to negative pi and pi?
It isn't. Why is omega limited between negative pi and pi? It isn't limited, right? I mean, it carries on. But, because cosine is periodic in omega equals 2 pi, it'll just repeat. And of course, as we know, the DTFT always is periodic in 2 pi. It repeats. Between minus pi and pi, it can be whatever it wants, but then it's going to repeat because it's periodic in 2 pi, because that's what happens when you take the Fourier transform of sampled signals that only exist at discrete uniform intervals. So, moreover, there's this whole argument about aliasing, that if I want to build a time domain signal, I can build it out of sinusoids with frequencies up to omega, which means I can build it out of complex sinusoids, e to the j omegas, but for omega between minus pi and pi. And if I go beyond that, those things, e to the j omega n for omega larger than pi, gives me the same values at n as one within that range, if I just subtract off 2 pi, then I get one that's in that range. And so that's why we only plot it between minus pi and pi. And in fact, if the impulse response is real, then it's going to be conjugate symmetric. So it's going to be, if I just know it from 0 to pi, then I can get it from minus pi to 0 because it's just going to be the conjugate of that. And so this is the part that we actually care about. Yeah. Yeah. Why don't, you mean the negative part down here? So why don't we focus on the negative part? So this is quite interesting, actually, that I said that the frequency response was periodic in omega equal to 2 pi, which means that it's going to be composed of things like cosine omega or some multiple, cosine k omega. Here we've got a frequency response that's actually cosine omega on 2, which is periodic in omega equals 4 pi, right? This is not going to complete a cycle until omega gets to 4 pi. So it's like, wait, you're saying the frequency response has to be periodic in omega equals 2 pi, but you're building it out of something which is omega equals, which doesn't repeat until omega equals 4 pi. But here you can see what's going on, because actually, I mean, the magnitude response, at least, because it's the rectified version, it's the magnitude of cosine omega on 2, has this thing where, yeah, okay, it's the cosine function is not going to loop, not going to get back to 1 until we get to 4 pi over here. But because it's rectified, actually, by the time we get to 2 pi, when the cosine function is at minus 1, the magnitude of the cosine function is at 1. So this magnitude of cosine omega on 2 is periodic in 2 pi. And it turns out that that's basically what's happening. It's not quite so clear here, but at the same time as you get this thing changing its flipping its sign here, this term is basically giving us an e to the j pi, which is a negative 1, and so it really is flipping the sign to make this whole thing periodic in 2 pi. What that means is just what that means is that there's an expression for this in terms of this shape, this rectified cosine omega, has a Fourier series representation. Sorry, this series magnitude of cosine omega on 2 has a Fourier series representation in terms of cosine omega, cosine 2 omega, cosine 3 omega, etc. You can express it in terms of cosine omega and its harmonics, but it has a lot of them because it's got a discontinuity in slope here, so it means it has a lot of high-frequency components. So it's just a mathematical convenience that we can express this thing without having to have a lot of terms, even though it's not, strictly speaking, we're not expressing it in terms of things that are periodic in 2 pi, but it turns out that the whole function is periodic in 2 pi, and because it has to be, and so the whole thing is valid. That's a very, very nice observation. And this comes up again when we talk about these the design of finite impulse response filters like this. They all have this trick where you end up looking at omega on 2 rather than omega because the whole thing is going to be rectified afterwards. Okay, but the point here is we've gone from the impulse response through the frequency response and seen that, yes, we understand what's going on here. There wasn't actually any design involved here because the filter was there's no parameters to that filter. We could scale the gain, but that would just be like multiplying the signal by a constant value before we put it through. However, we can talk about characterizing what the filter was to, say, distinguish different kinds of low-pass filter. If you have a one-parameter characterization of a low-pass filter, it's going to be the cutoff frequency, which is, the idea of a low-pass filter is that the gain goes down as frequency increases. And so we choose some particular amount that the gain's gone down by and say what frequency it sort of crosses that threshold. And by convention, the threshold is a magnitude of 1 on root 2, which means that the magnitude squared, which is the power, is halved. So it's sometimes called the half power point. And we can solve for the omega c where this occurs by plugging in our magnitude of h v theta j omega. So here's our magnitude of h v theta j omega. It's cosine omega on 2. And so if we solve for that equal to a half, then we find, if we equal that equal to the square root of a half, then that turns out to be omega is pi on 2. So here's the plot. Here's our magnitude response. Here's our value, 1 over root 2, a half power point. And it turns out that's actually also halfway to the highest frequency here. That's a pi on 2 where the highest frequency is pi. So that's the omega c for this filter. Yeah?
So which one is the amplitude of the impulse? Like which one is it the...
Which one is the amplitude of the
like,
impulse? So we designed this filter to have amplitude of a half, and that means that we get this particular Fourier transform, right? If we'd made them 1 and 1, then this 2 would have disappeared, and then actually when we sum up the eta j omega and eta minus j omega, we would have got 2 cosines, so there would have been a scaling factor of 2 in here. So the reason we chose a half here is just so we get a scaling factor of 1 in here, which means that, for instance, at omega equals 0, cosine omega on 2 is 1, eta minus j omega is 1. So we get, for omega equals 0, for DC, for a constant input, we get a gain of 1, exactly 1, right? And if it had been 1 and 1, then the gain would have been 2. So here, in terms of the cutoff frequency definition, it's sort of normalized. So you assume that you've got your peak gain here normalized to whatever it is, to 1. And if it's 1, then we're interested in the gain at 1 over root 2. If it was k, then we'd be drawing the line at k over root 2, but the picture would look the same. It would just be the scaling of the vertical. I mean, but by convention, we always, if we want to canonicalize a filter, then we say, okay, let's choose a frequency where its gain is going to be 1. For a low-pass filter, you assume you'd normally use DC as the reference frequency.
So it's not like the analog domain where you have like before you get to the 3 dB point, the magnitude is 1, and that's after that it starts going down.
It can be. So it can be like, it's even in analog filters, the gain is only ever. It's not always. It's not always 1, right? It's going to be varying depending on the shape. If it's monotonic, then it's only going to be 1 at a certain frequency, at the 0, basically. If it's got ripples, then we'll see that. So there are different definitions, but typically, actually, the definition we typically use is the peak gain in the passband. But it's just conventions. It doesn't matter that much. One of the reasons that we use one of the things about using the half power point is that a lot of the equations work out nicely for simple filters. But in general, you can do whatever you want. It's just a convention. So, okay, we've seen that we're interested in magnitude. I've several times already plotted magnitudes on a logarithmic scale. The interesting thing about that was that now there's this nice symmetry between poles and zeros, that poles are the things that have infinite gain plus infinity gain, and zeros have gain of 0, but if we take the log of that, then the log of plus infinity is still plus infinity, maybe not pushing quite so hard, but it's still infinite. But now the log of 0 is now negative infinity. And so now we have this kind of symmetry. And so, but the nice thing about a log scale is that if you have detail close to 0, it sort of gets magnified out. And very often we are interested in details close to 0 because even though the gain may be much less than 1, it may be that, well, we really need it to be a lot, we need it to be 1,000th or 1,000,000th or something, and you can't really see those on a plot where you've got 1 as well. So we very often use this log scale, and rather than just using raw logs, we use decibels. Again, this is a convention, but it's a convention that makes sense. The convention for decibel is that it's 20 times log base 10 of the level, or 10 times log base 10 of the power, because power is proportional to level squared. And the nice thing about this particular scale is that the numbers, the things that we care about, tend to be sort of in the range of natural numbers. That the 0 to 10 dB is kind of a useful range, whereas if we just used log base e, then there'd be some strange thing. But this is a convention that comes from a time when people were doing these things in their head or pencil and paper, when they cared about what the values were, and that's what we talk about. If we calculate what our half power point corresponds to in the decibel scale, we're saying the magnitude at cutoff is 1 over root 2 of the magnitude, the peak magnitude. So we take the dB of this, which is just taking the 20 log 10 of these things, the 20 log 10 of a product is the sum of the 20 log 10s of their two things. And so we end up with this term here, 20 log 10 of 1 over root 2, which works out to be negative 3.0103 something. And so it's very close to being negative 3. And so now half power in decibels corresponds to 3 dB down, minus 3 dB. And so that's why you hear the sense of a 3 dB point or something like that, because it's just the same. It's the same idea as a half power point. And then if we actually plot the graph, here's our magnitude response between 0 and pi in terms of linear gain, 1 at 0, omega equals 0, and 0 at omega equals pi, radians per sample. Here's our 1 over root 2 half power point. On a dB scale, well, the gain of 1 corresponds to a dB of 0, because log of 1 is 0, even base 10. The gain of 0 corresponds to a dB of negative infinity, right? So we sort of falls off the bottom of the plot. We could make this axis as long as we liked, because there's always more negative numbers we can get, but typically we care about a range of a few tens of dB, right? Minus 20 dB is 1/10. It's the dB of an amplitude gain of 0.1. And now the log, right, which log expands the low and compresses the high. So this nice sinusoidal curve turns into this kind of more round-looking curve where these have been squeezed out and these have been stretched out. And then here's a half power point, 3 dB point, which is still at the same frequency, but now it's just the intersect with minus 3 on this graph. So most often when we're plotting magnitude responses, this is the way you'll see them in terms of dB. Okay, so that was, one simple filter, the low pass, and we now know how to analyze it in terms of these different tools that we've got. So let's look at another simple filter. This is, again, an FIR filter, but this time we're looking at a high-pass filter. And the impulse response is like this. It's plus a half, minus a half. So it's like the same, but we flip the sign of the second point. Still only a 2-point filter. We do the Z-transform, and all that's happened is that this has become 1 minus e to the minus 1 rather than 1 plus e to the minus 1, which means that the 0 is now at z equal 1 rather than z equal minus 1, with this pole at 0, which we're going to ignore. But here's our pole 0 diagram. Because we've got a 0 at omega equals 0, we're going to have a magnitude response that starts off at 0 here. It's going to have a gain of 0 for dc. And then actually you can sort of, again, by thinking about the vector length, you can see that it's going to have a maximum gain when we're at omega equals pi, this sort of highest frequency we can get before we go into aliasing land. And indeed, here it is. And if we do the actual solution, again, we can split out the e to the j omega on 2, and we get 2j sine coming out, and 2 gets cancelled out here. So we get j, e to the j omega on 2, sine omega on 2. So it's kind of interesting. The magnitude response is now just a rectified sine rather than a rectified cosine. We've got this linear half-sample delay, as I characterized it last time. We've also got this term here, j, which is e to the j pi, right? So we've got a pi. We could have written this as e to the minus j of omega 2 minus pi or something, right? It would have been the same thing. So we've got this extra constant offset in our phase response, which is, a 90-degree phase shift for those of us, if we've looked at those kinds of things before, which comes from this kind of high-pass filter. And again, that's typical, but that's what it looks like in this domain. We can characterize high-pass filters by their 3 dB point, which is, again, the frequency at which the gain is 1 over root 2 of the peak gain, which here is at omega equals pi. And in this case, again, as we know from the symmetry of the sine function, it also occurs at pi over 2. Yeah?
Is it possible to just look at the z-plane and say, oh, this is a low pass or this is a high pass?
Absolutely. Is it possible to look at the z-plane and know that it's whether it's a low pass or a high pass? Yes. This is obviously a high-pass filter because it's got zeros, which is the places where the gain is minimized. They're around the low frequency. And the other one, which had the 0 over here, that means that it's going to have less gain around the high frequency. Now poles the other way around, right? Poles close to a point mean the gain is going to be large here. So a high-pass filter would have poles around here and not around here. And a low-pass filter would have poles around here and not around here. And of course, you can have combinations of poles and zeros, as we'll see in a second. But that's what you're looking for. A low-pass filter has its zeros around its zeros around z equal -1, and its poles around here, and vice versa. So just to sort of make an observation about these two filters, the low pass and the high pass. Here's the low pass, a half. Here's the high pass, a half minus a half. They're clearly quite closely related. One way we could express the relationship between them is to say, well, the high pass filter is the impulse response to the high pass filter is the impulse response to the low pass filter multiplied by a 1 minus 1, 1 minus 1 signal, minus 1 to the n. Of course, there are only two non-zero points, so there are a lot of functions that are 1 at 0 and minus 1 at 1 that we could have written down. But this is an interesting one to look at because this is a sinusoid, right? This is modulating onto a sinusoid. Or if we expand it out in the z domain, that the what is the z transform of this in terms of the transform of this? So sum of this times z to the minus n, we can fold the minus 1 into the z to the minus n, and we actually get that hh of z is just hl of negative z. Right? The z transforms would work if I just make a substitution for the z. What that means is that to get the value of hh for some point on the z-plane, I could go to my hl on the z-plane. I just take the negative of z, which is to flip it in the real axis and flip it in the imaginary axis, and then just read off the value. So if I have the entire hl plane here, I can build the entire hh plane just by flipping and then flipping, which is actually the same as a 180-degree rotation. And so that's what I try to show with these colors here, that in the HL plane it goes purple, blue, green, yellow, orange. In the HH plane, if I go, it starts off over here and then goes around like this, right? So it's the same plane but rotated by 180 degrees. Of course, if I rotate by 180 degrees, if I rotate, the unit circle maps onto the unit circle. It's just that the values change. And so the frequency response, or the Fourier transform of these two things, it's the same set of values. It's just where they start and end that changes. And so here's our magnitude of HL, which is this low pass going to 0 at pi and then back up. Here's the magnitude of HH, which is the same shape but shifted by pi radians, which is what I just said. It's a shift of 180 degrees of pi radians, a rotation of that, which is just shifting the frequency response relative to each other. So this is not how we would figure out what this is. We can figure out what this is directly just by taking the z-transform. But it's interesting to note that we could have interpreted what's happened here, the relationship between these two filters, as a rotation of their z-transforms, a rotation in the z-plane. Which raises the interesting point that we can think about rotating by other angles, and sometimes that's something that we're going to do. And we can also, this whole idea of understanding what's happening in the z-plane as a function of the z variable as like affine transformations on the entire plane. We will come back to that. Let me just see. Let's just look at one IIR filter before we finish, just so we've. Oh man. The lecture picks up, I think, after these. So let's look at this IR filter. Okay. So now we've dealt with two very simple FIR filters. Now we're going to deal with an IIR filter, an infinite impulse response filter, a filter with feedback, with poles. And so here is our very simple first order IIR filter. Here's the output, the delay, and the feedback. We're also going to put an input delay here. We're going to put 1, 0 on it just to make it, we didn't have to, but that makes it nicer behavior. And so this block diagram, from here we can write down what yn is in terms of x of n minus 1, and y of n minus 1. We can get our difference equation out. We can take the z transform, and we get this z transform equation expression for the system. And we see that this thing here gives us a 0 at z equal minus 1 here. And this thing here gives us a pole at z equal alpha, where alpha is now a parameter for our filter. So we actually have a family of filters here, which could be one of these values out here. We have an overall gain k here, and that's just a scaling of the whole thing. But we can use that. It doesn't appear on the pole zero diagram, of course. Pole zero diagram doesn't specify overall gain. But we can use that just to sort of to normalize the gain of this magnitude response, and we can use it to set the gain equal to 1 at omega equals 0, or at z equal 1. So we can just figure out what k that would be by substituting z equal 1 in here, which would be, so z equal 1, we get 2 on 1 minus alpha. So if we make k equal to 1 minus alpha on 2, then this whole thing will have a value, a magnitude of 1 at z equal 1, which means it has a gain of 1 at omega equals 0, dc. So if we do that, we can get magnitude responses like this. They're always 1 at 1, and they die away to 0. They've got to be 0 at omega equals pi. But it turns out that as we vary alpha, we get this variation in the response. And basically, the closer alpha gets to the omega equals 0 point, the sharper this peak gets, right? We're getting further and further up on that big pole mountain. We're slicing it closer and closer to the sharpest point. We're normalizing down, so the gain stays the same, but the low-pass filter becomes more and more selective, more and more narrow. And we can see the 3 dB point is reducing. So the cutoff frequency of this low-pass filter is changing with alpha. If we plot the same thing on a log plot, so this is both in dB and also log frequency, then it actually looks completely different, but it's the same function. But now we can sort of focus in both on these, we can focus in on the detail close to 0 in here, and we get this set of responses here. But the same trend, which is that as alpha tends to 1, the cutoff gets lower and lower in frequency. But here's the nice thing, right? So here's our equation. If we want to try and calculate the cutoff frequency, we can plug in the magnitude response equal to the maximum on 2. The maximum is going to be 1 if we use our k as specified. To get this magnitude squared, we can just multiply the complex gain by its conjugate. So the gain is 1 plus eta j omega, 1 plus eta minus j omega c on 1 minus alpha eta minus j omega c. We can conjugate that just by changing the e to the minus j omegas to the e plus j omegas. So this is h conjugate, and then we've got k and k conjugate. K is real, so k and k conjugate is just k squared here. We end up with an equation here in terms of eta j omega c and alpha, and we're trying to solve for when that is equal to a half. And that basically, if we do the trick of converting the eta j omegas into cosines, it's going to work out because this thing is going to give us a real answer. We get an expression in terms of cosine omega c and alpha, which we can then turn around to give us alpha in terms of omega c. And now we've actually got a design equation. We've got this family of functions with this parameter. Let's say we want to achieve a particular omega c. We just plug in the omega c, it gives us an alpha, and we get a filter that does what we wanted. And that's kind of the whole point of this exercise, which is like, okay, in practice, I've got a task. I need a filter of a particular kind. I want to be able to just implement that filter without having to play with it. And so I can use an equation like this to design it. I'm going to have to leave it there. Let me just say quickly. I feel like I haven't quite boiled this down to the bottom of okay, how do we solve problems on this? But this is the idea, right? That I can specify a real system. Someone can give you a filter which has some coefficients, some alphas and betas, and then you can answer questions about what it's going to do with frequencies by this whole process of calculating its Z transform and its Fourier transform, and then evaluating the Fourier transform at different points. And you can do that backwards as well. So someone can give you a frequency response or a set of constraints in the frequency domain. you can then have your equation for the Fourier transform and figure out how to set the parameters of your system to get what you want. And that's kind of the whole, that's the loop, that's the whole point of all these tools. Any questions? Okay, we'll look out for the email confirming the details about next week. And as I probably won't see you before then, unless you want to come to office hours tomorrow, good luck in the test.